In the winter of 1991, on the cold concrete of RAF Waddington, a sound that had defined British aviation for half a century finally went quiet. An Avro Shackleton maritime patrol aircraft shut down its four massive engines for the last time. This was the early 1990s. It was an era of stealth technology, fly-by-wire computers, and the quiet reliability of the modern turbofan. Yet resting on the Lincolnshire tarmac was a machine still driven by a World War II-era piston design. The engines ticking as they cooled in the freezing air were Rolls-Royce Griffons. They were 36.7-liter, 12-cylinder, liquid-cooled blocks of aluminum and steel, capable of producing well over 2,000 horsepower. When the Royal Air Force finally retired them, they were not merely withdrawing an old aircraft. They were severing their last operational link to the sheer mechanical violence of the heavy piston age. For the RAF mechanics who had kept them running, the final shutdown meant the end of a very specific kind of labor. It was the end of wrestling with heavy spanners, fighting relentless oil leaks, and enduring the deafening, bone-shaking vibration that gave the Shackleton its nickname, the Growler. The military service network was finally handing the skies entirely over to the turbine. The paradox of the Griffon is one of absolute mechanical brilliance overshadowed by cultural memory. It was physically larger than the Rolls-Royce Merlin. It was vastly more powerful. It served in frontline military roles for decades longer. Yet while the Merlin became a romanticized national myth, the Griffon was largely left behind in the historical record. But the real story of the Rolls-Royce Griffon is not only the story of a late retirement, it is the story of how Britain built its ultimate piston engine, only to watch it get swallowed by the shadow of the Merlin and the dawn of the jet age. Every week, we tell the stories of British engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place, in Derby, in the late 1930s. In the late 1930s, the town of Derby was already defined by the noise of testing. Inside the Rolls-Royce engine plant, the V12 Merlin was being prepared to defend Britain. It was a 27-liter masterpiece that would soon become the sound of the Royal Air Force. But inside the drafting rooms, the engineers understood a brutal rule of internal combustion. There is always a limit to how much power can be squeezed from a given size. The Air Ministry, the government department controlling British military aviation, knew that aircraft would inevitably become heavier. They would need more armor, more fuel, and heavier weapons. To pull that weight through the air, Britain would need a larger power unit. Rolls-Royce had an existing blueprint for massive power, the R-type racing engine, which had won the Schneider Trophy and pushed British seaplanes to world records. But a racing engine is a fragile, highly stressed instrument. Britain needed a military workhorse. The new project was named the Griffon. The brief was to create a larger, stronger V12, a 12-cylinder engine with cylinders arranged in two banks in a V shape. The target was to increase the displacement, the total volume swept by the pistons inside the cylinders, from the Merlin's 27 liters to a staggering 36.7 liters. This created an immediate physical crisis. An aero engine, an engine built for aircraft use where power, weight, reliability, and certification matter differently from road vehicles, must not only be powerful, it must be aerodynamic. In a fighter aircraft, the nose must be as narrow as possible to reduce drag. If an engine is 36% larger in capacity, the block and cylinder heads naturally become wider. A wide engine creates a blunt nose, pushing a wall of air that cancels out the advantage of extra horsepower. To solve this, the Derby engineers executed one of the most brilliant mechanical packaging feats in British industrial history. They had to keep the massive 36.7-liter block within the same physical silhouette as the much smaller Merlin. The secret lay in the camshaft, the shaft that controls valve opening and closing, dictating how the engine breathes. In the Merlin, the drive mechanism for the camshafts and the magnetos was located at the rear of the engine block. This made the back of the Merlin relatively bulky, taking up vital space right in front of the pilot's bulkhead and forcing the aircraft designer to widen the fuselage. For the Griffon, Rolls-Royce designers moved the camshaft drive and the magnetos entirely to the front of the engine, tucking them neatly behind the propeller reduction gear. This single, highly complex decision transformed the Griffon. It kept the rear of the engine narrow and clean. It allowed the heavy 37-liter monster to retain a frontal area that was almost identical to the 27-liter Merlin. The block was longer, and it was significantly heavier, but looking at it from the front, it cast the exact same aerodynamic shadow. It was a retention of grace hiding an enormous increase in violence. Development accelerated in 1939 as the reality of a European war became undeniable. Interestingly, the initial push for the Griffon did not come from the fighter squadrons of the RAF, but from the Fleet Air Arm, the aviation branch of the Royal Navy. Naval aviation presented a completely different engineering problem to high-altitude dogfighting. A naval aircraft had to operate from the short, pitching deck of an aircraft carrier. It required massive, instantaneous torque. Torque, the twisting force often felt as the pulling strength of an engine, is what tears a heavy machine away from gravity before the runway runs out. The Fleet Air Arm wanted the Griffon for the Fairey Firefly, a heavy naval fighter. They needed the 36.7-liter displacement not for high-altitude speed, but for low-altitude muscle. In the foundries of Derby, workers began casting the massive aluminum crankcases. Machinists cut the heavy steel crankshafts, which had to be stiffened and redesigned to handle the immense firing impulses of the large cylinders. The factory floor was dominated by the sheer scale of the components. The physical reality of the Griffon was intimidating to anyone who worked on it. It required larger coolant pumps, heavy-duty oil scavenge systems, and a complex supercharger, a mechanically driven device that forces more air into the engine, allowing it to burn more fuel and make more power at higher altitudes. Every component was scaled up, yet confined within a strict spatial boundary. On the assembly lines, the Griffon block sat on engine stands like iron and aluminium monuments to British industrial anxiety. The engineers knew that whatever aircraft eventually received this engine would have to be heavily modified to handle the weight and the rotational stress. By 1941, the first prototypes were running on the test beds, shaking the concrete mounts with a deeper, more resonant vibration than the Merlin. The sound was distinct. It lacked the high-pitched scream of its predecessor, replacing it with a guttural, throbbing roar that vibrated through the floorboards of the Derby plant. The fuel consumption was heavier, the parts were bulkier, and the service manuals being drafted for mechanics were thicker, detailing a machine that was fundamentally less forgiving to maintain. Yet the achievement was undeniable. Rolls-Royce had successfully packaged the displacement of a heavy bomber engine into the aerodynamic profile of a nimble interceptor. They had built a machine that could deliver over 1,700 horsepower in its earliest forms, with the architectural strength to handle well over 2,000 horsepower as development continued. It was a masterpiece of metallurgy, machining, and spatial problem-solving. The block was ready. Britain still had to decide what kind of machine could physically handle that much power. By late 1942, the Royal Air Force faced a brutal mechanical reality over the English Channel. The German Focke-Wulfs FW-190 had arrived, and it was systematically outclassing the Merlin-powered Spitfire Mk5. The British fighter was suddenly too slow, too heavy in a dive, and lacking the sheer acceleration required to dictate the terms of aerial combat. The Air Ministry needed an immediate counterpunch. They did not have the time to design, test, and certify an entirely new airframe for the front line. Instead, they turned to the sheer, blunt force of the Griffon. The result was the Supermarine Spitfire Mk2, issued first to number 41 and number 91 squadrons to intercept low-level, high-speed German hit-and-run raiders. It was the first operational British fighter to be powered by the new 36.7-liter power unit. When these aircraft began arriving at frontline RAF airfields in 1943, they did not look drastically different from their predecessors, thanks to the brilliant packaging of the camshaft drive at the front of the block. But the men tasked with flying and maintaining them immediately understood that this was an entirely different machine. To understand the breakthrough of the Griffon, one must understand displacement, the total volume swept by the pistons inside the cylinders. The Griffon was nearly 10 liters larger than the Merlin. In practical terms, this meant it could draw in, compress, and ignite a vastly larger volume of fuel and air with every rotation of the crankshaft. This did not just create more horsepower, it created an overwhelming physical amount of torque. Torque, the twisting force often felt as the pulling strength of an engine, is a phenomenon that a pilot feels directly through the airframe. In a heavy motor vehicle, torque is what pulls a load up a hill. In a lightweight World War II fighter, torque tries to twist the entire aircraft around the axis of its own propeller. The Spitfire Mk weighed roughly 7,500 pounds. The Griffon engine produced so much twisting force that on a damp grass airfield, the sheer application of the throttle could tear the wheels loose from the ground and violently throw the aircraft off course. This immense torque created the most famous and dangerous quirk of the early Griffon-powered Spitfires. For years, British pilots had been trained on the Merlin. The Merlin's propeller rotated clockwise when viewed from the cockpit. To keep the aircraft pointing straight down the runway during takeoff, a pilot instinctively pushed their left foot forward on the rudder pedal to counteract the twisting force pulling the aircraft to the right. It was a reflex built into a generation of airmen. But the Griffon's crankshaft, the rotating shaft that turns piston motion into rotational power, spun the opposite way. The Griffon propeller rotated counterclockwise. When veteran pilots climbed into the Megantunun for the first time, they opened the throttle and the massive block delivered its power. Out of sheer habit, they applied heavy left rudder, but the Griffon was already pulling the nose to the left. The combined force of the engine's torque and the pilot's incorrect rudder input caused Spitfires to violently swerve off the runway, sometimes scraping their wings on the tarmac or tipping entirely into the grass. The breakthrough engine required the British service network to retrain its instincts. The airfields had to rewrite their manuals, placing strict warnings in the cockpits. The old rules of power no longer applied. You could not fly a Griffon on Merlin muscle memory. Once in the air, however, the Griffon proved its worth against the V12. At low and medium altitudes, the immense displacement allowed the Mk to accelerate with a ferocity that the German fighters could not match. But to maintain that power as the aircraft climbed into thinner air, the engine relied on its supercharger, a mechanically driven device that forces more air into the engine. Because the Griffon had such massive cylinders to fill, the supercharger impeller had to move an astonishing volume of air, drawing heavy amounts of power directly from the crankshaft just to spin it. It was a complex, heavy piece of engineering that required constant monitoring from the pilot and intense maintenance from the ground crews. For the mechanics in the dispersal huts, the Griffon was an intimidating piece of equipment. It required larger spanners, heavier lifting gear, and a deeper understanding of its complex systems. The magnetos, now relocated to the front of the block alongside the camshaft drive, were easier to access but required meticulous timing. A mechanic working in the freezing rain of a British winter had to ensure that the spark ignition fired at the precise millisecond to ignite the massive volume of petrol inside the 36.7-liter cavern. The cooling system, a critical network of pumps and radiators designed to keep the liquid-cooled V12 from destroying itself under its own heat, was under immense pressure. The Griffon generated significantly more heat than the Merlin, and managing that heat on the ground before the airflow of flight could cool the radiators was a constant struggle for the ground crews. Yet they trusted it. They trusted the heavy iron and aluminum castings. The sound of the Griffon became a new kind of comfort over the coast of southern England. It did not sing or scream, it growled. It was a deep, guttural thudding sound that vibrated through the chests of anyone standing near the runway. It was the sound of maximum British industrial effort concentrated into 12 cylinders, turning petrol into violence to protect the airspace above them. The Griffon had done exactly what it was designed to do. It had taken an existing aircraft and brutally forced it back into a position of aerial superiority through sheer mechanical displacement. It had solved the crisis of 1943. The Griffon had proven it could dominate the sky. But the sky itself was about to change. The arrival of the Supermarine Spitfire MiG-14 in early 1944 marked the absolute peak of British piston engine fighter development. The Rolls-Royce Griffon had evolved from a heavy stopgap into a refined instrument of extreme speed. The 36.7-liter V12 was now fitted with a two-stage, two-speed supercharger, a highly complex mechanical compressor system that forced dense air into the cylinders at two different gear ratios, allowing the massive block to breathe efficiently from sea level all the way to 30,000 feet. The performance figures shattered previous expectations. The Griffon 65 series could reliably produce 2,050 horsepower. It pushed the Mecklenburg-Vorpommern Spitfire to a verified top speed of 448 miles per hour. In the hands of No. 610 Squadron, the Griffon transformed the Spitfire from a defensive interceptor into a machine that could outclimb and outrun almost anything in the European theater. But this power was most desperately needed, not in the freezing altitudes of bomber escort missions, but just a few hundred feet above the English countryside. In the summer of 1944, the V-1 flying bomb campaign began. These early cruise missiles thundered towards London at low altitudes, traveling at around 400 miles per hour. The Merlin-powered fighters struggled to build enough speed at such a low altitude to catch them. The Griffon did not struggle. With its immense displacement and low-end torque, the Mk14 could dive, level out, and physically run down the V-1s over the fields of Kent and Sussex. Pilots pushed the throttles to the firewall, demanding every ounce of power the heavy crankshaft could deliver. The engine blocks ran incredibly hot, the exhaust stacks glowing a dull cherry red in the twilight. But the iron and aluminium held together. Griffon-powered squadrons accounted for hundreds of intercepted flying bombs, relying entirely on the brutal mechanical displacement of the 37-liter engine to close the distance. Yet the glory of the Griffon was not just experienced in the air. It was paid for on the ground, in the dispersal huts and concrete aprons of frontline airfields. For the RAF mechanics, maintaining a Griffon 65 was an exhausting physical battle against heat, vibration, and complexity. Every component of the engine was heavier and under higher stress than the generation that preceded it. The cooling system, a critical network of radiators and pumps designed to stop the liquid-cooled V12 from melting itself under its own friction, was constantly pressured by the massive heat rejection of the large cylinders. The mechanics had to wrestle with 24 spark plugs, deeply recessed in the wide cylinder heads, often working on them while the block was still radiating the fierce heat of a combat patrol. Oil leaks were a relentless reality as the immense internal pressures of the 2,000 horsepower block forced lubricants past gaskets and seals. In a Britain where an engine could decide whether an aircraft lifted from a grass airfield, a lorry made its delivery, a motorcycle carried a rider through the night, a bus left the depot, a racing car survived the next lap, or a luxury car kept its silence at speed. Power was not an abstraction. It was metal, fuel, labor, heat, sound, repair, risk, and trust. The men in the oil-stained overalls at bases like RAF West Malling understood this better than anyone. They trusted the Griffon not because it was elegant, but because its architecture was undeniably strong. They learned to tune the complex carburetor, a device that mixes fuel and air before it enters the engine, to handle the massive gulp of petrol the 36.7-liter displacement demanded. They managed the intricate ignition harnesses, ensuring that the engine did not misfire under the immense boost pressures of the supercharger. This mechanical trust extended beyond the airfields of southern England and out into the pitching, saltwater environment of the Royal Navy. The Fleet Air Arm had driven the original requirement for the Griffon, and by the late stages of the war, they relied on it heavily. The Supermarine Seafire, the navalized version of the Spitfire, was notoriously difficult to land on an aircraft carrier. But the Griffon-powered variants, particularly the Seafire F-Mk15 and later the Mk47, gave naval aviators the sheer, instantaneous torque required to pull away from a botched landing. When a pilot was waved off by the deck officer, they needed immediate pulling strength, not a gradual buildup of speed. The Griffon delivered that pulling strength the millisecond the throttle was opened. The Derby engineers had created a piston engine that seemed to have no limits, dominating both the sky and the sea. But the machine was about to collide with a physical boundary that no amount of displacement could overcome. As the horsepower figures climbed ever higher, the Griffon created a new mechanical crisis. The 36.7-liter block was producing so much twisting force that a standard propeller could no longer absorb it. If the engineers at Derby simply bolted a longer propeller to the crankshaft, the tips of the blades would break the sound barrier, losing all grip on the air and creating a deafening, inefficient shockwave. If they added more blades, moving from 3 to 4 to a massive 5-bladed unit, The sheer rotational mass created terrifying torque reactions that threatened to flip a lightweight fighter on a narrow runway. The solution was an engineering marvel that defined the ultimate peak of British piston aviation: the contra-rotating propeller. By designing a highly complex reduction gearbox at the very front of the Griffon block, Rolls-Royce engineers could drive two separate propellers on the exact same axis, spinning in opposite directions. For the mechanics tasked with maintaining it, this gearbox was a masterpiece of metallurgy and a nightmare of complexity. It was packed with heavy-duty gears, bearings, and high-pressure oil seals, all designed to transmit well over 2,000 horsepower without tearing itself apart under the strain. On the flight line, a Griffon-powered Seafire Mk-47 equipped with these contra-rotating propellers was a completely different animal. The torque was entirely neutralized. A pilot could open the throttle fully on a damp aircraft carrier deck, and the machine would track perfectly straight, but the sound was unforgettable. The guttural, throbbing roar of the heavy V12 was now overlaid with a harsh, tearing shriek as the opposing propeller blades sliced through each other's aerodynamic wake. This was the absolute physical limit of the internal combustion aero engine. In the late 1940s, the Griffon 85 series was pushing towards 2,400 horsepower. Supermarine built the Spiteful and the Seafang, fighters designed with new laminar flow wings to take the Griffon to its absolute theoretical maximum. In testing, they approached 490 miles per hour. Every casting, every valve, and every connecting rod, the part that links the piston to the crankshaft, was subjected to stresses that would have seemed impossible a decade earlier. The foundries in the Midlands were pouring aluminium and machining steel to tolerances that represented the absolute ceiling of wartime and post-war industrial capacity. The Griffon weighed nearly 2,000 pounds. For the ground crews, changing one in a freezing hangar required heavy gantries, massive spanners, and a team of men working in unison to align the massive block with the airframe mounts. This perfection came at a steep logistical price. The maintenance burden on the RAF and Fleet Air Arm Service networks was immense. The engine required massive quantities of high-octane aviation petrol, specialized lubricating oil, and constant adjustment of the complex ignition and supercharger systems. A mechanic could spend hours just tuning the fuel delivery to ensure the massive cylinders did not run too lean and melt their own pistons at altitude. The supply chains were stretched, delivering heavy spare parts to squadrons scattered across the globe. In the hangars and on the concrete aprons, the Griffon was deeply respected, but it was rarely loved in the way the simpler, lighter Merlin had been. It was too heavy, too loud, and too demanding. Yet as it sat on the engine stands in the repair shops, gleaming with fresh oil and safety wire, it was undeniably the most capable piston engine Britain had ever produced. It was the absolute pinnacle of British piston engineering, and that is exactly why its time was running out. The first crack in the Griffon's absolute dominance was not a mechanical failure. It was not a flaw in the aluminium castings or a weakness in the heavy crankshaft. The crack was the physical limit of the atmosphere itself, exposed by the arrival of an entirely new way to fly. By the late 1940s, the Air Ministry understood that the piston engine was trapped. The Griffon could be pushed to produce more horsepower, but transferring that power to the air required a propeller. As a Griffon-powered fighter approached 450 miles per hour, the tips of its propeller blades were approaching the speed of sound. At that velocity, the blades lost their grip, creating a wall of aerodynamic drag and a shock wave that violently shook the airframe. The engine had more power to give, but physics prevented the aircraft from using it. At exactly this moment, the Gloucester Meteor was proving the viability of the gas turbine, an engine that uses spinning turbine stages and high-speed gas flow to produce power or thrust. Instead of using a complex supercharger and heavy pistons to turn a shaft, the new Rolls-Royce Derwent jet engines simply inhaled air, compressed it, burned it with paraffin, and blasted it out the back. They produced thrust, a forward-pushing force created by accelerating exhaust gases, without needing a propeller at all. For the fighter squadrons, the calculation changed overnight. A jet engine was mechanically simpler, required vastly less oil, and suffered no propeller tip drag. It flew faster, climbed steeper, and did not try to twist the aircraft off the runway with immense torque. Fighter command no longer needed the massive displacement of the Griffon. The market for ultimate British piston speed had vanished. In a normal industrial cycle, this would have been the end. The Griffon would have been retired, relegated to the history books alongside the biplane in the fabric-covered bomber. But the British military service network had one remaining problem that the early jets could not solve: the Atlantic Ocean. The Royal Air Force's Coastal Command needed a new maritime patrol aircraft to hunt submarines. This aircraft had to fly low over the freezing ocean, carrying heavy radar equipment, depth charges, and a large crew. Most importantly, it had to stay in the air for up to 15 hours at a time. Early jet engines were incredibly inefficient at low altitudes, burning through fuel so fast that a jet-powered patrol plane would have to turn back almost immediately. What the Air Ministry needed was not thrust, but endurance and heavy load-pulling capability. They needed the Griffon. The result was the Avro Shackleton, a massive 4-engine maritime patrol aircraft that first flew in 1949. Instead of powering a lightweight fighter for an hour of frantic combat, the Griffon was now tasked with dragging a heavy bomber airframe across the ocean for over half a day. Each Shackleton was fitted with 4 Rolls-Royce Griffon 57A engines. That meant every aircraft carried 146 liters of piston displacement, driving 8 contra-rotating propellers. It was an overwhelming concentration of mechanical force. And for the crews who flew it, and the mechanics who maintained it, it became a brutal physical trial. The Shackleton quickly earned the nickname the Growler. The noise inside the unpressurized fuselage was not merely loud, it was physically destructive. The deep, guttural throb of 4 massive V12 engines was layered beneath the high-frequency, tearing shriek of the contra-rotating propellers slicing through the air. For the pilots, navigators, and radar operators sitting inside, the vibration penetrated their bones. Air crews returning from a 15-hour patrol over the North Sea would step onto the tarmac entirely deafened, their muscles aching from the relentless shaking of the airframe. Over the decades, permanent hearing loss became a standard occupational hazard of the Shackleton fleet. The mechanical toll was equally severe. The Griffon had originally been designed for short, violent bursts of interceptor speed, not for grinding out 15 hours of continuous low-level flight in salt-heavy air. The engine blocks ran hot. The immense internal pressures caused the massive crankcases to flex slightly, destroying oil seals. Oil leakage was not a rare fault, it was a fundamental characteristic of the aircraft. Shackletons famously left thick black puddles on the concrete aprons of RAF Kinloss and RAF St. Mawgan. In the air, the flight engineers had to constantly monitor the oil pressure, transferring heavy, viscous lubricating oil from reserve tanks to the engines, just to keep them from seizing mid-flight. Sometimes a mechanic would have to crawl into the wings during a mission to address a leak, or try to coax a failing generator back to life while the aircraft bounced through Atlantic storms. On the ground, the servicing burden was staggering. To keep one Shackleton operational, the ground crews had to manage 144 valves, 48 spark plugs, and 4 incredibly complex contra-rotating gearboxes. In the depths of a British winter, working on freezing dispersal pans, the mechanics waded through grease and aviation fuel, wrestling with heavy spanners to keep the obsolete piston architecture alive. They looked across the airfields and saw their colleagues working on sleek, modern jet bombers like the Avro Vulcan. The jet mechanics worked with clean components, swapping out entire turbine modules with relative ease. The Griffon mechanics were stuck in an older, dirtier world, fighting a daily war against friction, heat, and raw mechanical wear. The Griffon had found a way to survive the dawn of the jet age, but the cost of that survival was being paid in oil, deafness, in the slow breaking of the men who kept it flying. The tragedy of the Rolls-Royce Griffon in the 1970s and 80s was not that it was a bad engine, it was that it had outlived its own industrial support system. Back in Derby, the Rolls-Royce factories had entirely transformed. The machine lines that once cut massive steel crankshafts and cast heavy aluminum blocks for piston engines were now dedicated to the clean, high-speed world of the gas turbine. The Avon, The Conway and the upcoming RB211 turbofans were the future. The Griffon was a ghost haunting the supply chain. Rolls-Royce had officially ceased production of new Griffon engines in 1955. Every single block that powered a Shackleton through the 1960s, 70s, and into the 1980s was a legacy item. This created a slow, suffocating crisis for the Royal Air Force service network. When an engine requires an overhaul, a major service process where an engine is taken apart, inspected and rebuilt to operating standards, it needs fresh bearings, new gaskets, and replacement valves. But the foundries were no longer pouring the specific alloys required for a 37-liter V12. The supply chains had dried up. To keep the Shackleton fleet in the air, the military had to rely on cannibalization. In the cold, echoing hangars of RAF Kinloss and RAF Lossiemouth, mechanics stripped down older, time-expired Griffons to salvage usable parts. The engine became a closed loop of recycled metal. A piston removed from a failing block in 1972 might find its way into another engine in 1979. The service manuals, once pristine documents of British engineering pride, became oil-stained, dog-eared records of a desperate rearguard action. The mechanics who worked on them, often older men who had trained on pistons or young fitters baffled by the sheer analog violence of the machinery, lived in a world apart from the rest of the Air Force. The Shackleton men were permanently stained with heavy lubricating oil. They spent their shifts wrestling with the massive, contra-rotating gearboxes, trying to keep the delicate balance of the opposing propellers in tune. When a Griffon fell out of synchronization with the other three engines on the wing, the resulting harmonic vibration could shatter glass instruments on the flight deck and leave the crew physically nauseous. Beyond the mechanical exhaustion, there was a growing logistical nightmare: the fuel. The Griffon required high-octane aviation petrol, a highly volatile and expensive fuel. By the 1970s, the world's military and commercial fleets had transitioned almost entirely to jet fuel. Aviation petrol was becoming a niche, expensive commodity. The Ministry of Defense had to maintain separate, costly fuel storage tanks and supply lines just to feed the thirsty V12s of the Shackleton fleet. The fuel economics of keeping the piston engine alive were failing. Yet they were forced to keep flying. The world around the aircraft had completely modernized. The Shackleton AEW-22, the airborne early warning variant, was tasked with patrolling the maritime borders of the United Kingdom during the height of the Cold War. Inside the heavily vibrating fuselage, operators sat in front of glowing radar screens, tracking modern Soviet nuclear submarines and supersonic bombers. Outside, dragging them through the sky, were 4 liquid-cooled piston engines designed to intercept Focke-Wulfs over Sussex. It was a bizarre collision of eras. The radar operators were looking at the digital future, while their ears were deafened by the mechanical past. The Ministry of Defense had long planned to replace the Growler with the jet-powered Nimrod AEW. But when the British Nimrod radar program suffered massive technological delays and budget overruns, the Griffon was forced to carry the burden even longer. It stretched its operational life far beyond anything the original draftsman at Derby could have ever imagined in 1939. It was a testament to the raw, over-engineered strength of the iron and aluminium. But no amount of mechanical durability could stop time. The British government eventually canceled the failing Nimrod AEW program and ordered the Boeing E-3 Sentry, an American jet-powered aircraft with modern turbofans and vastly superior radar. The order meant the end. The market for ultimate British piston power was not just dead. Its long, painful afterlife was finally over. There would be no more overhauls, no more recycled pistons, no more 15-hour patrols deafened by 12 cylinders of combustion. The transition was absolute. The engine still ran. The parts supply died. The aviation fuel grew too expensive. The repair hours climbed. The radar screens flickered. The jet alternatives arrived. The final orders were given. The hangars fell quiet. The sound vanished. The badge remained. The Britain it protected was gone. The Rolls-Royce name did not disappear. In the decades that followed the retirement of the Shackleton, the company that built the Griffon transformed into a global aerospace giant. The Derby plant, which once deafened the Midlands with the roar of heavy V12 piston engines on the test beds, became a facility defined by the sterile, high-bypass hum of the RB211 and the Trent turbofan engine families. The company survived, but its identity as a builder of massive piston aero engines died entirely with the Griffon. The era of pouring heavy aluminum crankcases and machining complex supercharger gears for frontline military use was over forever. Today, the Griffon survives outside the mainstream industrial economy. It is kept alive by a deeply committed British preservation and enthusiast community. At the RAF Museum in Hendon, at the Imperial War Museum in Duxford, and at airfields across the country, the remnants of this 37-liter empire are carefully maintained. The Battle of Britain Memorial Flight still operates the Supermarine Spitfire PR-Dunning, relying on the Griffon to pull the late-war reconnaissance aircraft through the modern sky. But the most visceral preservation happens on the ground. At Coventry Airport, preservationists have spent years fighting to keep an Avro Shackleton WR963 alive. They do not fly it, but they maintain and run the Griffons. When those four engines are fired up for a crowd, the concrete physically shakes. The mechanics who maintain it must navigate a vanished supply chain. They rely on oil-stained service manuals, original parts catalogs, and a shrinking network of specialist suppliers to find the heavy-duty gaskets, valves, and spark plugs that Rolls-Royce stopped making decades ago. The engine has moved from a military necessity to a deeply demanding industrial antique. This survival is not merely nostalgia. A Rolls-Royce Griffon sitting on an engine stand in a British hangar is not just a romantic echo of the Second World War. It is a physical argument about a specific moment in British manufacturing history. It proves exactly how far British industry could push the internal combustion engine before the laws of physics forced a complete surrender to the turbine. It shows the absolute extreme of analog mechanical engineering, a time when solving the problem of speed meant adding more displacement, heavier steel, more complex gears, and more heat, rather than writing a new line of software. The Griffon has always suffered from a unique cultural problem. It was forced to follow a national hero. The Merlin became the romanticized voice of British salvation, heavily associated with the Battle of Britain and the summer of 1940. It got the poetry, the films, and the public adoration. The Griffon arrived later, larger and louder. It did the brutal, unglamorous heavy lifting at the end of the war, and then dragged maritime patrol aircraft through freezing Atlantic storms for another 40 years. It earned respect, but it rarely earned love. If you look at the physical sites where the Griffon was maintained, the contrast with the modern era is stark. The freezing, oil-soaked concrete dispersal pans of RAF Kinloss and RAF Waddington are now used by highly digitized, jet-powered maritime patrol aircraft. The modern mechanics working there plug diagnostic laptops into the engines to read fault codes. The brute force labor of the Shackleton men, wrestling with massive spanners to adjust a contra-rotating gearbox in the freezing rain, has been entirely replaced by a culture of module replacement and cleanroom engineering. Yet there is a strange footnote to the Griffon's afterlife. Long after the British military had relegated the engine to maritime patrol duties, the sheer over-engineered violence of the block found a new home. Because the Derby engineers had built the bottom end of the engine to withstand unimaginable stress, the Griffon became highly prized in unlimited air racing and hydroplane boat racing. Competitors discovered that the engine could be heavily modified, stripped of its complex high-altitude superchargers, and tuned to produce over 3,000 horsepower for short, brutal sprints. An engine designed to hunt German fighters in 1943 ended up roaring across pylons decades later, simply because its foundational iron and aluminum were too strong to break. Ultimately, the Rolls-Royce Griffon did not fail. It was not beaten by a better piston engine, nor was it brought down by a lack of British manufacturing skill. It was defeated by the speed of sound, the aerodynamic limits of the propeller, and the invention of the jet engine. It was a machine that did exactly what the Air Ministry asked it to do in 1939, and then kept doing it long after the world had decided it was no longer necessary. Britain did not stop needing power. It simply stopped needing power that looked, felt, and sounded like this. The Griffon represents the terminus of a bloodline. It was the heaviest, most powerful, most uncompromising V12 piston engine the country would ever put into frontline military service. When the last Shackleton shut down its engines in 1991, it was not just the retirement of an aircraft. It was the end of an entire philosophy of British mechanical force. Today, the skies are quieter, cleaner, and vastly more efficient. But somewhere in a cold British aviation museum, a 37-liter Rolls-Royce Griffon still sits silently under the display lights. Its massive aluminum crankcase is dulled by time. The complex gearbox rests immobile, and a faint smell of heavy lubricating oil still lingers around the cylinders. A massive, dormant monument to a time when Britain built its power out of pure, deafening thunder. See you in the next video.